Today we're going to be talking about the banked turn type of problem. The banked turn type problem is a classic in physics, and in this case what we have here is we have a car on a turn, so it's like a NASCAR, right? NASCAR race. And this car is either coming at us or going away from us, and it's on a banked turn. So we kind of visualize it like that. If the car is like going away from us and on a banked turn, we can kind of visualize this. And it says, draw a force diagram and label it for a car attempting to drive around the turn without turning the steering wheel. Now that seems like a weird thing. Like, how could you take a turn without steering? Well, it turns out that if you want to take a turn without steering, the whole road itself has to be curved. So visualize the fact that you don't need the tires in the road to push you in. What you have is you have the whole road pushing you in. So let's draw a force diagram for that. Here's a dot that represents the car. And we have the earth pulling it down. We call that the weight, and we represent that with a little mg, m being the mass of the car, and g being the gravitational field strength. And then we have the road pushing perpendicular to the road surface. So if this is the force, we call this the normal, that's the perpendicular. It's pushing in this direction. And really, those are the only two forces that we have acting on the car if we don't need any friction. So in an idealized sense, you could actually take this turn if it was all icy. And we actually have examples of that because we watch bobsled and luge all the time where those are on ice and they're able to take those turns. So it's a visualization of that. It's a little too short. Let's make it a little longer. There, that's better. Okay, so in this case, this is the normal force, and this normal force pushes the car up and to the left in our diagram, and so we know that there's a portion that is up and there's a portion that is to the left, and that makes a lot of sense to me. I'm going to label these. This is the normal force in the y direction, this one is the normal force in the x direction, so we have a good sense of that. So this is all you need if you want to take the turn, is you need these conditions. So this normal force in the y direction balances the weight. So your unbalanced force is in the x direction, it's to the left, and that's inward on my car, and that is okay with me because if you're going around a circle, you need an unbalanced force toward the center. So this all seems to work out. The question is now, how fast could the car go and take the turn without turning the steering wheel and still stay in the same lane? So again, what we're going to do is we're going to use a Newton's second law statement for this car here and see if we can't come up with a statement to describe the speed. So let's talk about these in two directions. So I have the net force. Let's do the y direction first. Well, it's equal to 0 because there's balanced forces and there's no acceleration in the y direction. So if I look at the net forces in the y direction, I have the normal force in the y direction minus the weight. If those are both the same and it's equal to 0, then I know that the normal force in the y direction is equal to the weight. And I'm happy with that. That makes a lot of sense to me conceptually. What about the x direction? Well, let's think about the forces, the net force in the x direction. Well, it's equal to ma, where a is the acceleration, m is the mass. But because we're going around a circle, we know that it's centripetal acceleration, so this is actually equal to mv squared over r. What I'll also notice is that the net force in the x direction, there's only one force in the x direction, and that is the normal force in the x direction. Therefore, the normal force in the x direction is equal to mv squared all over r. I'm okay with that. That looks pretty good. So I'm feeling pretty good about this because I have a v, so that's what I'm actually solving for, and I have some other things over here. I think I know the mass of the car. Maybe we'll be able to work this out here. So how are these things related? Well, a little bit of geometry will tell you that this angle right here is also the same as this angle right here, and I wonder if these things are related. Well, I know that if this is my n in the x direction, it would also be this here, would also be the n in the x direction. So relative to this angle, that's the opposite, and this one's the adjacent. So I wonder if I can relate them through the tangent. So tangent theta is equal to the ratio of the opposite side to the adjacent side. In this case, the tangent of my angle is equal to the n in the x direction divided by the n in the y direction. And look what happens here. I have an expression for the n in the y direction here and the n in the x direction here. So if I substitute those in, I end up with mv squared over r divided by mg. This simplifies to the tangent of my angle is equal to v squared over rg. Now this result in itself is very interesting because what it tells us is that the mass of the car doesn't actually even matter, because it somehow magically disappeared in this here, and I guess that's kind of cool because it says that if this is a NASCAR race, the mass of the car doesn't even matter. The speed would still be dependent just upon the angle and the radius. So if I go to solve for this, v squared is equal to rg tangent theta. So v squared v is equal to the square root of rg tan theta. And then you can plug and chug and you can get an answer for the speed. Okay? You get an answer for the speed. And I'm feeling pretty good about that. The question is now, how would the driver feel? Would the driver feel heavy, light, or normal? Well, I wonder, in terms of this, whether the driver would feel heavy, light, or normal. Remember, we don't feel our own weight. What we feel is the normal force. So in this case, if this was just a force diagram for the driver or for the car, but if you think about it for the driver, what he's feeling is the seat push up on him. And I notice that this normal force here has to be the hypotenuse of my triangle, which means that the normal force in the y direction and the weight have to cancel each other out. This normal force has to be bigger than the weight, so I'm thinking he's feeling heavier. And I wonder if we can get a sense of why he feels heavier. Okay? Let's finish this right here in case we need it. V is equal to the square root of, according to the problem, the radius is 150 meters, our g value is 10, the ramp angle is 31 degrees, so it turns out V is equal to 30 meters per second. We might need that in a moment, so let's see if we can't. Okay, so let's reset and see if we can figure out how heavy he feels. So in order to figure out how heavy you feel, and again, he feels heavier because the normal is bigger than the weight, I'm going to take the ratio of the normal force to the weight. That's going to give me how heavy he feels. So if these were the same, we'd have a 1 divided by 1, he would feel normal. If this were twice as big, then he would feel 2 times heavier. So if we can get a value for the normal force, I think we're good to go. So let's go back, and if we look at this, I know that the normal force in the y direction is equal to mg. The normal force in the x direction was equal to mv squared over r. And so what we're going to do is, if I want to find the actual normal force itself, is going to be the hypotenuse of this triangle. So I'm going to say that the normal force is equal to the normal force in the x direction squared plus the normal force in the y direction squared. Well, the normal force in the x direction is the centripetal force. That's mv squared over r, all squared, plus the normal force in the y direction is equal to mg, all squared. And if we plug and chug a little bit, we may be able to come to some kind of value here. So this is going to be m squared times 30 squared divided by 150 squared plus m squared g squared. So as you plug and chug this is 30 squared, and then you have to square it again because it was mv squared squared, and then you divide here. And what I end up with is I end up with this statement here, where I have this whole thing turns out to be 36 m squared plus 100 m squared. And so according to this, n squared is equal to 136 m squared. If I take the square root of both sides, I end up with n is equal to 11.66 m. If I go back and I get my statement here, if I get the how heavy statement, I have to take the ratio of the normal force to the weight. So let's do that. So normal force divided by the weight is equal to 11.66 m, all divided by mg. And here again, g is my gravitational field strength, which we're going to use a value 10. And so 11.6 m divided by mg, the m's magically disappear, and you end up with 1.17 times heavier. So to me it's very interesting to go around this track. You would feel like scared because you're going like 200 miles an hour, but at the same time you're always feeling heavier than you are normally. Now it's not a ton, but it's enough that I think it would be significant and take its toll on the drivers over like a 2 or 3 or 4 hour car race. The last part of this question is actually very challenging. So we're going to have to reset completely. Because what we have now is it says, what's going to happen if, okay? What's going to happen if you're going faster than that minimum speed, faster than that 30 meters per second? How is you're going to have to turn the wheel? So if you're going to have to turn the wheel, you're going to have to add some friction to the equation. So according to the problem, it says, in the best possible conditions, the coefficient of friction between the tires and the track is 1 Newton per Newton. How fast could you go and still take the turn under those conditions? Well, we're going to need a completely new force diagram, because now, as we go to draw the forces on here, what we're going to have is we're going to have our weight again. Here's our earth force. So this is our mg. We're going to have our normal force again. So it's still, again, it's still perpendicular to the track. It's still in this direction. But this time, if you turn the wheels, you're actually getting a force in that direction. So as you want to turn, you turn your wheels so they're pointing down. So the wheels actually turn against the track up and push the car in the down direction. So here's your normal force again, and this time you have a frictional force in this direction. So this is going to be your frictional force. These aren't drawn to scale. We're going to see why the scale's wrong here in a second, but this is a good enough representation because this one is now up and to the left, where this frictional force is to the left and down. So now we have the normal in the y direction, the normal in the x direction, the friction in the x direction, and the friction in the y direction. If we look at the geometry, the way this looks, if this is your angle theta right here, this is also your angle theta, and this one in here is your angle theta. And so we're going to have to do some Newton's second law statements. We're going to have to do some Newton's second law statements to see if we can't simplify. So let's start with the x direction. The net force in the x direction. Well, what do we have in the x direction? We have the F in the x direction and the n in the x direction. So I know this is equal to mass times acceleration. Again, it's a circle, so it's mv squared over r. the net force in the x direction is equal to the F in the x direction plus the normal force in the x direction. Now, I know they're to the left, and a lot of times we use left as the negative direction, but this time we're using them as positive because we know they add, and everything's to the left. So we're using positive acceleration to the left, positive forces to the left. This is an N. If I look at this, how do these things relate to the angle is the question. Well, the F in the x direction is the adjacent side, so the net force in the x direction is actually equal to F cosine theta. So the F in the x direction is the F cosine theta plus the N in the x direction, this is then normal force sine theta. And then we end up with this statement that mv squared over r is equal to F cosine theta plus N sine theta.